Good afternoon. I'm Dan Carnovale. I'm with Eaton out of Pittsburgh, and I run what we call our Power Systems Experience Center there. I'm going to use some examples from that facility and show you how we're doing just this, training the next generation of workers in the electrical industry. So I think you've all seen those. So just a real quick thing about Eaton. We basically deal with all of the industries that you guys work with, and I think it gives us the opportunity to talk across all of the different segments. And what I'm going to show you today is how we train electricians specifically to work in those industries and what we're doing to give examples and try to train people through visual learning. What I get to do on a daily basis is I get to sit in this place in Pittsburgh, which we call basically an amusement park for electrical engineers and electricians. And it's kind of fun. Basically, we get to play with electricity all day. It's kind of a safe way. And we get to blow stuff up. Who doesn't like to blow stuff up, right? We get to cause problems, and then we get to show how those problems can be solved. And I started that particular part back in 2005, and we now have several experience centers around the country. One in Houston that focuses on oil and gas, and now we've kind of integrated some other things, data centers, commercial industrial applications. And we have one in Raleigh that focuses on data centers specifically, like on a bigger piece. And then we have one that focuses just on lighting, and that's in Atlanta. So the idea, I've kind of been inspired by the way that the IBEW does training with the hands-on sort of visual learning. And I've actually worked very closely in the past 10 to 12 years with our local 5 in Pittsburgh to kind of help them develop some training tools, and they've also helped me to develop some training. So talk to you a little bit about what we have there. Why is this important? The importance is really that we have a declining workforce, and I don't think that's any surprise to anybody. A lot more people retiring. We're seeing it in Eaton, frankly. A lot of the people that knew a lot of stuff are moving on. And we have a little bit of a problem with that handoff of information to the next generation. So what we're trying to do is we're trying to figure out how to do that better. The good news is that electricians and the need for electricians is growing. So we have less people. We need more of the same. So how do we make it better for those people that are coming into the industry, and how do we train them to make sure that they're ready, to do the job? It's interesting. I had 2 calls this morning while I was in the hotel because they forget that there's a 3-hour difference. So, I woke up at 4:30 anyway, but I got 2 calls this morning asking me electrical questions, and they were electricians from the Pittsburgh area. One of them asked me a question, and I'll get to it in a little bit, about a capacitor bank, why the fuses were blowing on this particular application. And another one was asking me a question about shorting blocks, for CT shorting blocks. And what I told both of them was based on examples that we've used in the Experience Center on a regular basis, on a daily basis. And I'll get back to that in a little bit. But what I want to tell you is it's hard to, over the phone, explain what might be going on with an electrical problem, electrical issue, without having something there in front of you to physically show you. Okay. It's interesting, we're going to talk a little bit about how we train. And in the industry, it's really funny. We hired about 20 electrical engineers, brought them into the Experience Center, and put them in front of a room that has about 13 different transformers and industrial and commercial kind of setups and all this kind of stuff. And we said to them, point to a transformer. You know what they did? They just kind of they looked around. Now remember, engineers aren't really trained to know what this stuff physically looks like. And then I draw that on a piece of paper, and they go, yeah, that's a transformer, right? But they have no physical idea what it looks like. And then we work with, again, the apprenticeship programs for the electricians, and they all tell me a different story. What they tell me is, we get, so I usually work with 2nd-year apprentices or 4th and 5th-year apprentices, and 2 weeks ago on a Saturday I had 1st through 5th from Steubenville, Ohio. So I get a lot of different opportunities to talk to electricians, and they all tell me kind of a similar story. What they say is basically this. We get into our jobs and we have really good mentorship programs and we learn along the way how things are done. And by the time we get done with our 5th year, we kind of know what a transformer looks like. Trust us. We've seen a lot of them. We've put wire, pulled wire to them. We've done a lot of digging around them, especially early on. And they all know what it physically looks like, okay? But what they tell me is the same thing. They say, you know what we do right before the power is turned on? What do? Right before the power is turned on any job, most of the time they do what? They go to the next job. Why is that important? The reason that's important is they don't get to see what might have been wrong, or maybe if there was a better way to do something, or let's say, not that they did something wrong, but let's say, going back to the guy that called me this morning, hey, we turned on that capacitor bank and the fuses blew. Why did they blow? I mean, did somebody size the fuses wrong? Are the capacitors bigger than they should have been? Or is there another problem? Maybe in this case, which I think happened in this case, was a harmonic issue with variable frequency drives that they had at the site. How would he know that, right? So what we're finding out is the electricians are looking for application type knowledge around the equipment that they're installing. The engineers are looking to figure out what this stuff physically looks like. I had a guy from US Steel, and he's a purchasing guy, but he wasn't either electrician or an engineer, but he said, you know what I think? He goes, when somebody hands me a bill on my desk and it says, $75,000, I think the electrical equipment's this big. And he goes, when it's $1 million, it's this big. And he goes, that's all I know. It's small, medium, large. He said, I have no idea what this stuff is. So having physical stuff, and again, inspired by the way that you guys do your training, I think is an important piece. So we're definitely looking to figure out the physical aspects of the stuff for the engineer side, but on the electrician side, we're trying to figure out, again, what could go wrong. What are the pieces of a transformer that, taps, regulation, things like that, phasing and running all the, and again, electricians will learn all this, and they do, and they know how to do it right. But a lot of times we'll explain to an engineer on site that decides to put all phase A, B, and C in separate conduits. They tell their facilities guy, it looks better that way, whatever, and then what happens? They melt something down, right? That's a problem. So you guys know that. They don't know that. So we're trying to bring the knowledge base better together, and that's what we do. So what we've done is we built basically an electrical neighborhood. So if you think about it, there's this road that kind of winds through there. We start at a utility substation, and we work our way around. There's a little retail space there, a little coffee shop thing. We have the substation in the background. We had to have a bridge because it's Pittsburgh. But we put a tree there, and it actually is up over the power lines. What we can do is we can actually make that tree fall into the power lines and cause a fault. And then when there's a fault, we turn on and off the power a few times with a recloser. Lightning storm going on. There's a lot of pretty exciting stuff going on. At the end of the day, it's how does all this stuff work together? Because, the components alone are fairly simple and straightforward to, again, put together and install. Is how do they all work together and sometimes not work together? That's the key point. As you wind around the road there's a home on the left. It gets into a kind of an oil and gas area on the right. There's a large switchgear room down the hall. There's what we call the power quality area on the other side. So every little piece of part has a training aspect around the applications, which again goes back to that higher level discussion of let's talk about how things work in the field. This one here, the power quality lab in an industrial area, we have basically along this wall are a lot of variable frequency drives, and what happens there is we actually feed those drives. It's a lot. So let me back up a minute. When I first started getting into this kind of training aspect of things, I used to work in the field a lot. I would do the troubleshooting, try to figure out problems. I got fairly good at working on solving the problems, and so then I started teaching classes around, hey, these are the kind of things to look for, these are the kind of things to look for. And I would literally go to hotels and do a session on how to solve electrical problems. So, for example, I would go to 25 different locations and maybe do like Seattle and Portland back to back. So we do maybe sometimes 50 a year. And what I do is bring little visual demonstrations with me to show people what things are. This was kind of a bigger version of what I used to do at that time, which was I would bring a little UPS with me, I'd bring a little surge protector with me and all that kind of stuff. This is the difference is that this is a full-scale version of that, but it's running real motors. It's 225 horsepower worth of motors through drives. It's a surge generator, literally to blow stuff up and show how surge protection works and does it. It's instrumented all the way around. So having that visual feedback of looking at the waveforms when something happens, and you can see, what does a meter look like when you sample 6 million times per second versus 128 times per second, and what are you missing when you go from one end to the other? There's a lot of different things you can see, and in particular in this we'll call it power quality lab. There's things on harmonics, power factor correction, which I know in Pittsburgh, the guys that come out after I think the second year and then sometimes into the fourth year, depending on where they're at, they're seeing this stuff that they just learned in class, and then it kind of reinforces what they just learned, because we're turning on a 300 horsepower motor and we'll show what the power factor is, and then we'll load up another motor and show how it changes as the loads change. So again, visual learning. The third part is with that area is with voltage sags and interruptions. So I've had a lot of end users come through there. We get about 6,000 people through a year, and a lot of end users come through and say, hey, I lost, one guy told me in particular, he lost $3 million in 1 year because of power quality problems. And so if we have, one of the electricians working on site there, and he tells them that, I want them to know, hey, we should think about the kinds of things I learned in this facility, in this particular lab. What I asked the guy was, hey, what are you seeing on your meters? And you know what he told me? He said, we don't have any meters. So I said, well, that's like going to the doctor and telling him, hey, doc, I have a problem, right? So then he takes out your appendix, right? Why would he take out your appendix? Well, you didn't tell him what your problem was, so he just does what he thinks might work. And he goes, well, if that doesn't work, we'll try something else. Put a cast on your leg. But the point is, the symptoms of the problem tell you what the problem is. So what we can do in this lab environment is we can actually simulate bad stuff happening, drives dropping out, things blowing up, problems like that. And actually, I showed that guy in particular a couple of those problems, and he said, yeah, that's exactly what we're seeing. We're seeing our HID lights in our warehouses go out. Well, that's probably a voltage sag issue. How do you fix that? Good, better, best ways to do that. But the thing is, identifying the problem is key. In this environment where we created harmonics, one of the guys that worked for me out of Pittsburgh from Ferry Electric there, he went out to a customer site, and the guys there were saying that they were having trouble with their power system. And what they did was it was one of these kind of buildings that kind of added on a whole bunch of stuff as they went, and they were printing checks for like payroll type stuff for a bunch of different businesses. What happened though was every time they would lose power from the utility, they would turn on their generator, and then they would run for a little bit, and then all of their UPSs would drain the battery and die. And he said it didn't make any sense. So what he was doing was he would go out and he would test the generator. And the generator looked good. How do we test generators? What do we put on? Load bank. And what's the load bank? It's a resistor. Resistor is a nice big heater, nice big, plain vanilla load, nothing too fancy. Well, what did he have on there as a real load? Under every single desk, he had a UPS. And all of those UPSs created what we'll call harmonics. And so what would happen is, picture this. You lose power, power goes off, the UPSs pick up the load. No problem. I'm still running all my computers on everybody's desk, okay? Generator kicks on. Generator says, I'm good, you can turn back over to me. So all the UPSs say, okay, I'm going to go back to you. They all go on the generator. Now that's kind of a harsh load to put on a generator. It screws up the generator, and they got up to over 20% distortion on the voltage. And so the UPSs would say, I don't like that voltage.
Design build using the latest technology.
So they would shut off,
trends and productivity.
and then they would go back to battery. Then the generator looked good again, then they go back and forth until finally the battery died. And what they had done was they put in, believe it or not, a residential generator, because they thought, well, it's, I only need like 40 kilowatts. I'll just buy the biggest residential generator I can put in. It was a really weak source. So that kid, he told me, he goes, I was thinking everything tested out right, but he goes, something in the back of my mind said it had to be related to something different than I was used to looking at. And so, to his benefit, he brought us in, and we created some filters that we put on, so no matter which side they were on, it worked fine. And we'll see those kind of things. But again, sparking sort of that knowledge around how's the world changing, what kind of things do I have to think about differently. Here's an example of some the data center environment. Uptime and efficiency are super important. And it used to be that I would talk to a lot of the data center owners, and it was funny because I one time tried to present a paper at a data center conference, and I asked them if I could present on efficiency. This was like 15 years ago. And they go, nobody cares about efficiency in data centers. Okay. Well, obviously you care about reliability, right? Uptime. But why don't you care about efficiency? Well, all we care about is keeping the servers on. It's at any cost, basically, right? Do you know how big some of the mega data centers are today? Like how many megawatts they are? They're like 100, 150 megawatts, okay? Now, if you watch Monday Night Football and the Steelers are playing, they'll still show steel mills because I think they still think there's a lot of steel mills around Pittsburgh, but there's not. But there's a couple. But anyway, it takes about 100 megawatts to make steel. So think about it. Data center here, steel mill. It's bigger than a steel mill, arc furnace. That's a big deal, okay? So now, if you're not thinking about efficiency and you're just throwing money out the window, that's a problem. So again, as we put in good, better, best versions of UPSs and all the components that go in data centers, without visually seeing why would I pick this one versus that one, you kind of want to see what the options are. We do a lot with switchgear. Obviously, arc flash is a huge deal. If we can dress somebody up in an arc flash suit, put them in front of gear, have them do all their testing and training before they're actually in front of real gear, it's, and again, you guys do that as an industry, but we're saying, there's again a lot of different changes in that aspect. So there's things like arc flash reduction maintenance switches. There's arc resistant switchgear. So again, how do I know if my customer asks me a question, and I'm the electrician on site, and I want to know what options do they have to make their systems better? Having exposure to it is important. And then of course we do residential applications, and that one is interesting. That room I've rebuilt 3 times in 10 years because it changes so rapidly. Now I know a lot of the electricians that are part of this group, right? We're working on commercial, industrial, and larger applications, but everybody has a home, and we all know that if you can put it this way, some of my management said, "Why do you have to show a home?" We're not. Yeah, we have a lot of residential customers and whatever, but they're all through contractors. Why do we need to show a home? I said, everybody that comes into the building has a home. If they can understand a transfer switch in their house, they can understand a transfer switch in a hospital. And it's again, scalability, right? I show a small residential CH breaker, and then I'll walk them in the other room and show them a VCPW, all right? That breaker is this big. It can feed 25,000 homes. So then you kind of show scalability, and then again, it's all about exposure. This one we've had some fun with, and I actually talked to Palmer Hickman, right? So, and I know Regina, you've talked. So we're talking about from the training group. We're actually going to have this simulator here mimicked for some of the stuff that the electricians will see. And what this is it's a water analogy. I'm sure a lot of you have tried to explain to somebody how does electricity work and you use water analogy, right? So current is similar to what? Flow of the water. And voltage is similar to what? Pressure. So we actually built, like a little simulator that the water flows through here with a pump, and we can show series and parallel resistors, we can show power, we can show voltage, we can show current, and this morning when I got a call, the guy was asking me a question, and I hate not having a whiteboard here to write on. I mean, it's just, but he asked me a question. He goes, so how do I explain? He was trying to train some people on what a CT shorting block was. Now, visualize this for a minute. Okay, a CT shorting block does what? You short out, you have your current transformer over here around the wire. As long as that's around the wire that's energized, it's putting out a secondary current that needs to go through a meter or relay or something, and it has to be looped, right? What happens if we open circuit that CT? Bad stuff, right? It can develop a big voltage, all right? So I was thinking I could use the water analogy. I could take current in form of water and flow it in a loop, right? And I just keep that going. That's my circuit. And then I have a valve all the way out at this end, all right? If I open that valve, bad things would happen, right? You get water all over the place. That's like open circuiting your CT, right? So how does a CT shorting block work? Somewhere along that path, instead of going all the way out, I develop a shorting path. I put another valve in, and I short the water out, right? Then if I open the valve at the other end, I don't get this crazy splash of water. Now, again, visualizing that, I can explain that to somebody in 5 minutes, and they can then take that back with them and go back and forth on how it works electrically. But there's a lot of things, like, has anybody ever had to explain to somebody what a kVAR is? Reactive power? That's, everybody uses the beer analogy, right? I know you're thinking of that, right? You're going to practice that later tonight. But that part of it is difficult to explain, and better yet, to teach, so or to learn. So this is a little workbench that we built for some of the students to work on, again, real loads and real things. So with the university, what we've done, and this is with Pitt, again, they don't know what the stuff physically looks like. We built 6 of these workbenches, and this actually has worked out really well. Again, the apprenticeship program has a lot of physical equipment. Universities have very little lab equipment, and what we found is that most of the lab equipment was donated 30 years ago, and it was 30 years old when it was donated. So they're working on stuff that's like never ever going to be seen ever in the world again. But it's in these labs. So, these poor kids don't know what they're missing. So we actually built some real legitimate simulators, and this is like, let's say, maybe like a 20th or somewhere between a 10th and a 20th of the size of the Experience Center as far as the load goes. Not the power quality lab part, not the whole Experience Center, but it works out well. So they'll put in resistors, reactors, capacitors, change power factor, they can put harmonics in, they can do motor starting with a 15 horsepower motor, soft starting, variable frequency drives, all of that stuff, and it all runs through these little benches, and then it goes back to a central location where they can then, centralize that power flow. Another very practical example of one of the things that we teach in the Experience Center is around surge protection. Okay, so one of the things we do is we'll blow up a light bulb, right? And we'll say, here's 7,000 volt transient, put an incandescent light bulb, which by the way are hard to come by anymore. But we put an incandescent light bulb in there and blow it up. Then we put a surge protector on there and show how it works. And I think even just sometimes that makes people feel better about buying and installing surge protectors. But then we put a meter on there and we show how it works and how well it works and how much it clamps and so forth. One of the most common things that we talk to electricians about is the lead length. So if this is the surge protector and this is the switchboard that it's connected to, that distance might be about 25 or 30 feet. And it looks good, and this thing is probably way over, they probably spend as much on that almost as this thing is probably a $15,000 surge protector. So frankly, they probably overdid it. But the fact is, the way they installed it, it's not even going to work. That lead length is really important, okay? So if you're going to install one in your house, when they say they have a clamping voltage, that means that if the voltage goes to 7,000 volts, it'll cut it off at a certain level, okay? Let's say it says it's going to clamp it at 400 volts, okay? That only works if the lead length is 6 inches, because that's the way they test them. They test them all at 6-inch lead length, and then if you go longer than that, you've got to do your own testing, okay? So what we show in the power quality lab is we'll do, and one installed on the bus inside the panel board. We show one that's 12 inches away, and we show one that's 3 feet away. So good, better, best, we'll show the one inside the panel is actually less than 400 volts because it's less than 6 inches. The one that's 12 inches away, for every inch of lead length, you get about 20 volts of let through. So it's 6 inches too long, 120 volts on top of the 400, 520, and it's pretty consistent. And then we put the one that's 3 feet away, 30 inches too long, 30 times 20, 600 volts on top of the 400 volts, it's over 1,000 volts. So imagine if it's 30 feet away, it's not even worth putting it in. Again, it looks really good, maybe that's the only physical space that's available, but the electrician doesn't know that it's not, and it's not his fault because they told him where to put it in, right? You know what he's going to now think about next time he goes out there? He's going to say, hey, I'm not even going to put this in. Why not? Well, it's not going to work. Why not? Okay, let me explain it to you. Let's find some space closer to it and make it electrically possible to do that. And then it's going to serve his customer better, her customer better, and at the end of the day, you're going to have, everybody's going to be satisfied, right? Because we get a lot of calls, hey, your surge protector doesn't work. And then we'll go out there and find out that, you know, it's way too far away. Or even better yet, the other thing that I always tell the electricians to come through, a lot of times people install them, what's the first thing you do right before you turn on the power? They high pot the system, they're looking for, you know, for grounded cables and stuff. They turn off the surge protector because if you high pot the system with surge protector on there, they're going to clamp with that and they're going to burn it up. So you turn it off. You know what usually they forget to do? Turn that back on. So a lot of times they go out, hey, your surge protector's burned out. The lights are off. This breaker, if you turn it on, you know. So, and again, it's not usually electricians that cause that, but they can find that. Again, they can be the hero when it comes back into it. One of the things that we're finding that people are super interested in lately is microgrids. So have you guys heard of the term microgrid? A microgrid is an application where you have, for two reasons. One, reliability, or the second, cost savings. You have a need to have your own power system. Let's say it's you know, a military base or a hospital, or even a feeder on a utility system. Like you might have a 5 or 10 megawatt system, and you might want to be able to control just that system, that part of the system, that load. So a microgrid is a good opportunity to do that. This is a full-scale microgrid and the 50 kilowatt size. But all of the components here, these little controller boxes, they're scaled, they're set up to run a 5 or 10 megawatt system. We just happen to scale it for our system there just so it shows real data. And in fact, what we have is, we have the utility source, we have a generator source, we have a battery source, and we have solar panels. You can have any and all of those. You can have even more, we can have any and more of those systems, and we can add in, let's say, wind or anything else. We're done at 20 hours. Yeah. Okay. So, I thought you were saying I had 2 minutes left. I was like, oh. Okay. But anyway, this is an example of, if you look at the green here, if you look at the green, that's the solar output. And as you'd expect during the day, you know, you get kind of a bell-shaped curve. The middle of the day is when we have the most, and we require the least from the utility, but we're actually locking in our load is changing a little bit over the day. Our storage, we're charging during the day when we have some available. Do you ever see a pump storage dam when they have a lake at the top of the hill?
Design build using the latest technology.
They have a lake at the bottom of the hill, and they run the water down with a hydro plant during the day. They generate electricity. They sell it for 12 cents a kilowatt hour. You know what they do at night? They pump the water back up to the top lake. Why? Because they can buy the power for 3 cents a kilowatt hour. So if I'm charging my batteries during the day, that's a good thing. Because if I have availability there, or on a day where I don't have solar, I can discharge them during the day to actually reuse that. So actually, sorry, a lot of times we're going to charge these overnight and discharge them during the day. This is actually showing the opposite of that right now. This one here is more of a typical solar pattern here. We're actually taking a shot there to fill up the storage overnight.